Hi, thanks for joining today. My name is Daniel Gysling of CorVera, and I'd like to talk about our CORx sonar augmented Coriolis technology for bubbly liquids. Coriolis meters are widely used in the oil and gas industry. The majority of these Coriolis meters are used on liquid applications where many of these applications are exposed to unquantified levels of entrained gas. Historically, entrained gases have challenged the operability and accuracy of Coriolis meters. Over the years, Coriolis manufacturers have made significant improvements in the operability of Coriolis meters on bubbly liquids. These improvements in operability have led Coriolis meters to be installed on applications exposed to entrained gas, such as liquid outlets of 2 and 3-phase separators. This exposure to entrained gas often results in significant, yet often unrecognized errors in mass flow, density, and volumetric flow. CorX is a minimally intrusive retrofittable technology that enables Coriolis meters to maintain near single-phase accuracy on bubbly liquids, enabling operators to more effectively leverage the advantage of Coriolis meters to achieve targeted accuracies in a broader range of applications. By enabling accurate mass flow, density, and volumetric flow of bubbly liquids, CorX effectively converts existing Coriolis meters into 3-phase meters for bubbly liquids. If we look at where Coriolis meters are used in the oil and gas industry, we find them being used throughout the process, from managed pressure drilling applications in which they play an important role measuring the wellbore fluids going into and out of the wellbore during the drilling process, to wellhead surveillance, test separators, production separators, export lines, LAC units, as well as applications where the flows are operating often near phase transition boundaries, such as LNG and CO2 applications. And if we, Coriolis meters come in many different shapes and sizes, but if we look at what's used in upstream oil and gas, we find that oil and gas almost exclusively uses bent tube Coriolis meters, and this is in part due to their well-known improved robustness in the presence of entrained gases compared to their straight tube counterparts. One of the applications we want to look at in more detail today is the application of Coriolis meters on the liquid outlet of separators. And here's just some data showing the prevalence of entrained gas in this is a compact gas liquid separator, but again, it could be any type of separator. But what we're looking at here is the application of a Coriolis meter for net oil, in which the density measurement of the Coriolis is the primary water cut measurement device. And the importance of this data really is just showing the prevalence of the gas void fraction coming out of the liquid leg of the separator over a 9.5-hour well test. That gas void fraction ranged between 0 and 4%, and that has if that gas void fraction is unrecognized and unmeasured, it can have a pretty serious impact on the accuracy of the net oil measured by the Coriolis-based water cut measurement in this application. In this particular data set, that 0 to 4% resulted in over 100% overreport of the net oil during that 9.5-hour well test period. We can take these Coriolis meters and take them into the lab and do a precise characterization of how they perform in the presence of gas void fraction. And here we have data from two different Coriolis meters. They're both 2-inch dual bent tube Coriolis meters, but they're different manufacturers. And what we find is they have different error characteristics over a similar range of fluid conditions. What we're showing here are the errors in density, shown in red, mass flow in blue, volumetric flow, shown in green, for these 2 meters over a range of gas void fractions for a range of different mixture volumetric flow rates. And what we find is for a given mixture volumetric flow rate through the meters, both of the meters have relatively linear characteristics. The errors in the gas void fraction, the errors in the Coriolis meter scale with the gas void fraction, but the size of the errors is a function of the mixture flow rate going through the Coriolis meter. And that is due to the mixture flow rate being a large factor in determining the bubble size of the gas bubbles within the bubbly mixtures, with the higher flow rates typically resulting in smaller bubbles and the lower flow rates resulting in larger bubbles, with the larger bubbles causing larger errors associated with a well-known error mechanism in Coriolis meters known as the decoupling effect. Our CORx systems will characterize the decoupling effect and correct for it. But if we look at what these, what the overall trends of the data are, is that Coriolis meters will produce errors on liquid flow rates that tend to scale within plus or minus several times the gas void fraction of the processed fluid through the Coriolis meter. These errors will typically be meter design specific, and they will be a function of the operating conditions of the meter. And it's data like this and other data sets that supports the often articulated hypothesis that unquantified gas carry-under is often the largest source of error in separator-based liquid measurements. So how does CorEx technology work, and how does it correct for the errors in Coriolis meters? Well, CorEx leverages over 25 years of sonar flow measurement technology that's integrated into Coriolis flow meter technology, and it's a patented and patent pending technology approach that leverages a pair of acoustic pressure sensors, one installed upstream and one downstream of the Coriolis meter, to measure the speed at which naturally occurring low-frequency sound propagates through the flow tubes of the Coriolis meter itself. The output of the two pressure sensors are interpreted using beamforming algorithms from underwater acoustics to determine the speed at which the sound is propagating, and then that measured sound speed then is used to determine accurately determine the gas void fraction within the flow tubes of the Coriolis meter itself. When we look at some data of the CorEx system being applied to the output of a 2-inch bent tube Coriolis meter operating over a range of bubbly mixtures, we find that the CorEx system is capable of reducing errors in mass flow and density by an order of magnitude. So a roughly 10x reduction in the mass flow density and volumetric flow on bubbly liquids. The CorEx system, because it's leveraging non-dimensional properties of the bubbly mixtures, can be calibrated on air and water mixtures, but then applied to a range of fluids out in the field, a range of oil, water, and gas mixtures, thereby enabling a practical approach to provide accurate measurements of separated base liquid rates independent of gas carry-under. Here's another example of the impact of entrained gas and gas carry-under on the performance of a Coriolis meter. This is a test at a multi-phase flow loop facility in which we're able to set a constant rate of oil, water, and gas going into the inlet of a two-phase separator. For this set point, we set a 50% water cut high GVF three-phase mixture going into the inlet of the two-phase separator, and then the liquid outlet of that separator was routed through a sonar augmented Coriolis meter, and that sonar augmented Coriolis meter was used to determine the water cut of the mixture. The gas carry-under of this from this two-phase separator is a function of the liquid level in that separator, as it is in most separators. And for this separator, when we're running at the higher liquid flow rates, for this set point, we could get down to a 0.5% gas void fraction. And then as we lower the liquid level of the separator, the gas carry-under increases, and then we're just adjusting the liquid level and separator over this roughly 15-minute set point, and we can vary the gas void fraction ranging from a low of 0.5% to a high of 2.5%. And we see the impact of that variable gas void fraction on the raw interpreted water cut. So if we just take the density output of that Coriolis meter and run it through the water cut algorithms based on the density of the oil and water, you would find that it's measuring water cuts between 45% and then ranging down to even below 30%. Again, due to this relatively small amount of gas void fraction between 0.5% and 2.5%. However, if you use a CORx, corrected or a sonar, if you use the gas void fraction to correct the output of the water cut, you can maintain the accurate water cut measurement independent of gas carry under at 50%. So if we look at the prototype system that we have for our CorEx system, we have and again, CorVera is a relatively new company. We're introducing the technology, but we do have a 2U rack-mounted prototype instrument, which leverages a pair of acoustic pressure sensors that are ATEX Zone 0 rated and rated to 8,000 PSI. Again, our system can be the pressure transducers can access the flow through existing ports if they're available, or we can utilize these industry standard bleed rings in order to make a pressure measurement immediately upstream and downstream of the flanges of the Coriolis meter itself. Our system does not affect the existing Coriolis meter in any way, so the operability is not influenced at all, and you will continue to receive the signals from the Coriolis meter that you were receiving before the installation of the CorEx system. But the CorEx system will report a gas void fraction measurement, and if we have access to the mass flow density and volumetric flow, we can report corrected mass flow density and volumetric flows as well. So, in summary, Coriolis meters are widely used throughout oil and gas liquid applications, and a lot of these applications are exposed to continuous or intermittent amounts of entrained gas. These levels of gas void fractions are typically unquantified and can often result in significant and yet often unrecognized errors in Coriolis mass flow density and volumetric flow rate. CorEx is a minimally intrusive retrofittable system that enables Coriolis meters to maintain near single-phase accuracy on bubbly liquids over a wide range of applications. And in particular for separator outlets, CorEx provides measurement surety by quantifying the separator effectiveness. It also enables separator optimization by providing a real-time monitoring of gas carry under levels, and really enables accurate separator-based measurement of oil, water, and gas through the liquid outlets of 2- and 3-phase separators. So CorEx effectively transforms existing Coriolis meters into a physics-based, fully transparent 3-phase flow meters for bubbly liquids. Thank you very much.